Hi everyone, Phil from statisticsmentor.com. Continuing on with the video about the hat matrix, now we turn to the properties of the hat matrix. Recall the hat matrix is defined by this, and here are the properties. Hat matrix is symmetric, idempotent, and positive semi-definite. Okay, recall what symmetric means. Take a matrix A, square matrix A. It's symmetric if the transpose is equal to itself. Idempotent matrix. Idempotent matrix means that if we take any powers of itself, say A times A square, it'll be itself. A cubed, it'll be equal to A, and so on. Positive semi-definite matrix. This is to do with quadratic forms. Quadratic form looks like this. So A here is, say, it's n by n, at least it's square, and these guys are vectors. 1 by n, n by 1, from which you can see that this quadratic form is 1 by 1. Positive semi-definite means that this value here, because it's a 1 by 1, is a value, is always going to be bigger than or equal to 0. And this is for any vector x, which could be 0, a vector of zeros, or a vector as well. It's worth mentioning that these two properties hold for any orthogonal projection matrices. And the other one that I introduced in the other video was related to h, was I minus h. So that holds also, these two also hold for this one. Okay, now we turn to the proofs for each of these three. The first two are easy, couple of lines of proofs. The third one we need another result. Okay, we start off with the proof of the symmetry property. We need to show that h is equal to the transpose of h. Okay, this is a exercise in basic manipulation then. So what happens here is that this is going to go down there and transpose. This whole thing is transpose, and this thing over there is transpose. Here we use the result. This result. Okay, and then this result, this thing here will be h if all this lot is x transpose x inverse, and it is because we can apply another rule here that you can interchange these two things. So it's transpose x transpose all inverse, and then here transpose, apply the rule again, from which you can see immediately it's just going to be x transpose x. That's the inverse, and this is h. Finished. Now I've shown you every step of the way here. Some people might leave out some of these steps, but I wanted to take care with the central one, because some people have difficulties with this central expression. Okay, next, h is idempotent proof. So what we just said, if the matrix is multiplied itself, it doesn't kind of change it. So let's square the thing. X. Alright, so these two here, that's h times h again. We note here that these two central ones, this one, since x is n by p, this is p by n, this is n by p, so they're conformable. And by the associative rule, we can multiply these two together. In other words, let's put the brackets to show that we're multiplying these two together as a group. But now look, take either this or this or this or this. You can see one is the inverse of the other. So if we take these two, you can see that is going to be the identity matrix of dimension n. Sorry, not by n, by p. By p. Identity subscript p. But anything times by identity is itself, so it's x transpose x inverse, x transpose, and that's h again. And then using this argument, you can see that for any power of h, it's going to be h. So we'll leave it there. Okay, finally the proof that h is positive semi-definite. For this we need to rely on the result. H is positive for any positive semi-definite matrix. It has eigenvalues that are non-negative. So let's take a vector w. Let's say hw equals lambda w, where lambda is the eigenvalue and w is the eigenvector for h. Multiply this expression 1 by h. We're going to have h squared w on the left, h w on the right, and lambda can come out since it's a scalar, so it can come. That's why I don't put h there, I put h there. But I cannot put h on the right of w because multiplying on the left is different to multiplying on the right when we're doing matrices. And from 1 we can see that hw is lambda w, so substitute that in expression 2. But since h is idempotent, we can see from here h squared w is equal to hw, and from 1 that is equal to lambda w. So we've got two expressions for h squared w, here in 2 and here in 3. So to equating them, it must be the case that lambda squared w equals lambda w. In other words, rearranging this, we must have this is 0, and that is the case if, so therefore lambda is equal to 0 or 1. In other words, we've just shown that the eigenvalues of this matrix H are non-negative, which is sufficient to say that it is positive semi-definite. More than that, notice that all eigenvalues are 0 or 1. And that completes the proof. Great, hope that's been helpful.